So, what if I told you that the key to building our high-tech future, everything from our smartphones to green energy, wasn't buried deep in some mine, but was actually hidden in these huge mountains of our own industrial trash? Well, it turns out a recent scientific breakthrough has found an absolutely brilliant way to unlock it, and we're about to see exactly how. Take a really good look at this. I mean, it just looks like simple, worthless dust, right? This stuff is called fly ash. It's basically just waste from coal power plants. But here's the crazy part. Locked inside these teeny tiny little spheres are some of the most valuable materials on the entire planet, and we are about to see how a flash of pure genius can get them out. All right, so before we get to the really cool solution, we've got to wrap our heads around the true scale of the problem we're facing. This isn't just about a few bags of trash here and there. We're talking about a challenge of planetary proportions. Get a load of this number. In 2023, China alone produced 899 million tons of just this one thing, fly ash. That's an amount that's almost impossible to even imagine, all from just one source, and it's piling up year after year after year. And it's not just the fly ash. We've also got red mud, which is this toxic gunk left over from making aluminum. And then there's the big one, the fastest growing waste stream on Earth, e-waste. All the phones, laptops, and gadgets we toss out every single day. We're literally creating mountains of modern waste. But here's where the story takes a really interesting twist. These massive piles of waste, they aren't just a problem that we have to manage. They're actually a resource, a mine, just waiting for us. They contain a hidden treasure. And that treasure is a group of materials called technology critical elements, or TCEs. You can think of these as the unsung heroes of our digital world. The rare earth elements, they make the super powerful lightweight magnets in things like wind turbines and electric cars. And gallium and germanium, they're the absolute foundation for the advanced chips that run, well, everything. Without this stuff, our high-tech society just grinds to a halt. And this is why it's such a big deal on a global scale. As this research points out, these elements are incredibly valuable, but the supply chain is, let's just say, it's fragile. It's often concentrated in just a handful of countries, and that creates these huge economic and geopolitical risks. So finding a new, stable, domestic source, it's not just a nice idea. For a lot of places, it's a matter of national security and economic stability. Okay, so if all this incredible treasure is just sitting right there in our waste piles, why haven't we been using it? Well, there's a pretty big catch. The elements are locked away tight. So here's the heart of the problem. The valuable metals are chemically fused inside these unbelievably stable crystal structures. The best way to think about it is like they're trapped inside a microscopic chemical cage made of silicon and aluminum. You can't just, rinse them out with water. You have to physically break the cage itself. This slide just perfectly lays out the old way of breaking that cage. And honestly, it's a story of brute force. The traditional method, it's called alkali fusion, is basically a checklist of everything you don't want to do. It uses tons of harsh, nasty chemicals, it guzzles huge amounts of energy, and it takes over an hour of intense heating. It's slow, it's expensive, and frankly, it's pretty dirty. But what if, instead of slowly and painfully melting that cage, you could just shatter it instantly? This, my friends, is where a jolt of genius comes in. Meet flash joule heating, or FJH for short. The concept behind it is actually pretty simple, but it is incredibly powerful. You pass an enormous jolt of electricity through the waste material, and that generates an insane amount of heat. We're talking up to 3,000 degrees Celsius in less than a single second. It's basically like creating a controlled lightning strike on a microscopic scale. And this shows you the setup. It's remarkably straightforward, right? You've got your waste material, you mix it with something conductive, like graphite, and you put it in a tube between two electrodes. That's pretty much it. Then, you just hit the switch. The whole thing really just breaks down into 3 simple steps. First, you mix the waste with some graphite powder, just to help it conduct electricity. Then, you load that mixture into the reaction chamber. And then, you flash it with a massive discharge of current. And the effect is immediate and just dramatic. This chart shows a really direct relationship. The more voltage you apply, the higher the temperature just skyrockets. You hit it with 140 volts and the sample hits 2,500 degrees Celsius almost instantly. To put that in perspective for you, that is way hotter than the melting point of steel. And here's what that blast of heat actually looks like. The sample just glows this intense white hot, all in the blink of an eye. This isn't slow baking in an oven. This is a thermal shockwave that literally rips through the material's chemical structure. And here is the result on a microscopic level. It's amazing. On the left, you see the original fly ash, right? With its smooth, spherical particles. That's our chemical cage. Now look at the right. After just a single flash, the structure is completely shattered. The cage has been obliterated, and all that treasure inside is now free and accessible. And it's not just a physical change either. Check this out. Here's that red mud. Before the flash, it's not magnetic at all. But after the flash, that intense heat has caused a chemical reaction. It's reduced the iron oxide to magnetic iron. This is just undeniable proof that FJH is fundamentally changing the material itself. So, we've broken the cage. We've changed the chemistry. What does all this actually mean for our future? Well, the implications are absolutely massive. I mean, the results really do speak for themselves. Using FJH, scientists can pull out over 95% of the rare earths, over 90% of the germanium, and about 80% of the gallium. These rates are just as good as, and in some cases even better than, those old, dirty, energy-guzzling methods. When you put the two methods right next to each other, side by side, the conclusion is just obvious. It's not even a contest. FJH uses way less energy, it's thousands of times faster, and it completely avoids all those harsh chemicals of the old process. It is simply a cleaner, faster, and way more efficient path forward. And a technology like this could fundamentally change how we view waste. Instead of being this costly problem we have to bury in the ground, these huge industrial byproducts become a valuable resource stream, kind of like an urban mine that we can tap into again and again for the materials we need to keep innovating. It's really an incredible thought, isn't it? Just by applying a jolt of creative energy, we can transform a huge problem into a solution, which leaves us with a final, fascinating question to think about. If we can do this with our trash, what other seemingly impossible challenges out there are just one flash of genius away from being solved?